Good afternoon, everyone. Welcome to week 4 of your technical lectures. I'm referring you back again to the spreadsheet branching system that you can see in front of you. Last week we started on this column of structural elements, and we looked specifically at this area here, what I call bearing elements, those part of structures that take load to ground in one way or another, load-bearing walls, columns and foundations. This week we're going to look at this part of the chart, what we call spanning elements. So as you can see from this diagram, I will upload this, by the way, onto Blackboard as a separate diagram, so you can print it out and put it on the ceiling above your beds. So spanning elements is broken down into two major areas: unidirectional and multi-span. The reason for doing this is, again, it kind of relates back to how the loads are carried back down to ground. All of these unidirectional spanning elements are effectively spanning from one point to another point laterally, if you like. That means that the loads are carried as if they're all bridges. You might as well consider them all to be bridges, although of course in reality you are designing mainly floors and roofs. And by the way, can I just get something off my chest right at this point, which is that when you think of the ground, yes, remember last week we looked at different foundations, and it is possible to cast one large concrete slab onto the ground, but it's not advisable, partly because it's a huge amount of concrete, it's a terrible waste of the world's resources, but also because if I were you, I would consider the ground plane to be a floor, always. Draw it as a floor, lift it off the earth or whatever is below you, and consider that the ground is a floor, is also spanning, is a bridge, is a platform. So here we are. Unidirectional spanning elements are either beams, so a number of single spanning beams that are then replicated, if you like, to make floors and roofs, or they are homogeneous with a kind of plate. So we're looking at these are what we call profiled plates, and we'll look at these. When we look at multi-span, we're then creating floors and roofs out of monolithic structures. When I say monolithic, I mean that these structures can be carried to ground at any point. They will cantilever, they can be carried at the center, or they can be carried at the edges. So it's a sort of different principle, if you like, and of course very common, because reinforced concrete is probably the most common way of creating floors and roofs in buildings. Nevertheless, so here we are. We call them bridges or platforms, or if you want to be specific, architecturally, floors and roofs. Let's look at beams. Now, we've already mentioned this when we were looking at stone columns, that stone, any kind of stone construction, whether it be piling stones to make load-bearing walls, whether it be carving stones to make columns, whether it be placing stones across from one column to another, stone is what's known as a low tensile material, as is brick, as is unreinforced concrete. And being low tensile, it cannot deal with long spans, because if you cast your mind back to the first lecture on structural physics, you will know that when you load a beam from above, or even the dead weight of the beam is putting pressure onto that beam, the top part of the beam is effectively compressing and the bottom half is being pulled in tension. If there is nothing in that material to resist that tension, it will eventually fail at a certain length. And here's a good example of it. This crack in one of the beams at the Parthenon has been stitched together using a steel tie, you can see here. You would expect the crack to be in the lower part of the beam, because even with this tiny little span, and it's only very short, it's only a couple of meters, the mass of the stone itself is forcing it to fracture and fail along this point here. So mainly we will use materials that can be loaded in tension as well as compression, and of course one of the ideal ones is timber. And many floors are assembled using a simple timber beam and repeating it throughout the structure. Here's a nice little example of the ground floor being a floor in itself. It's sitting on these little elegant little concrete pads every so often, which are taking, so you can see there's a kind of substructure or beam along here, and then these lateral ones crossing orthogonally from the main structures along that way. When it comes to steel, you will have probably, wherever you are from in the world, you might have come across these sorts of construction components. In this country we call them I-beams for obvious reasons, and the I-beam is designed specifically to resist load in terms of the depth of this is known as the web, and in terms of the flange which stabilizes the overall structure and makes it a monolithic object. So again, you don't need a steel beam to be solid throughout this cross section. You only need the web, which is taking most of the load, and the flange, which, as I say, is making it a stable structure. Okay, and when we're designing I-beams, we need to know the width of the flange, we need to know the depth of the web. Now, I-beams are not necessarily steel. The same principle. Here's an engineered timber version of the I-beam, where you've got a piece of sawn timber along the top, sawn timber along the bottom. These are and the web is actually OSB oriented strand board. It's a particle board that, as you can see, it's a man-made particle board. And again, similar structure again. This kind of construction technology, we'll go into it more when we look at timber generally, is becoming more prevalent and common in the construction industry because, of course, timber and very few other materials are the only materials on the planet that are sustainable in so much as they can keep reproducing themselves. All other materials are finite. So this, which is known as an engineered timber I-beam, will become more common. You can even have a glass I-beam. This is glass and aluminium, very elegant way of carrying load. But the same principle applies. Here's the web, here's the flange. This has been a very common way of putting floors together over many years. It's known as a beam and block floor, as you can see there. Most of the loads are being taken by these precast concrete elements, and they're not I sections, are they? They're sort of an upside down sort of a T. You can see the sort of T section. That's taking the most of the load, and because it's got this slight edge, this flange here, we're dropping in lightweight concrete blocks in between the two to make the continuous surface. It's a very common way of, as I say, very cheap and very simple way of putting a floor together. You're not pouring concrete, are you? You're getting precast blocks, which are probably precast beams, which are probably you might have to crane them in, but it might be possible for a couple of people to lift them. Certainly these lightweight blocks can be lifted and put into place. What do you notice about these T-section beams? Well, of course, what we're looking at here, you see these little holes? These are the rebars, the reinforcing steel, which again, as you would expect, is predominantly in the lower part of the beam, taking the tensile load there. So they're cast in to the precast concrete beams. And just out of interest, again, if you did happen to be in the Marylebone Road campus and you were in our block, you would be working most likely on this level here, which is the 4th floor. My office is on this floor, and I'm looking up into these rather lovely, elegant roof lights on either side. And you can just about see how the structure works from this image, can't you? As I said to you before, there are big shear reinforced concrete shear walls every so often along the length of the building, and these are bridges. They're not. They are cross section. This is a beam that's doing that job of spanning from this wall to the one on this side. This is doing the same. So these are all beams of one kind or another. Continuous cross section, reinforced concrete in this case. And of course you won't see it in this drawing, but linking these underneath are a series of little drop stand concrete beams that link the two together to make the overall structure work. Now, as I said to you, I think in the lecture on structural physics, the key to spanning is that the longer the span, the deeper the section of the beam. Whether it's an I-beam or any other type of beam, there is a strict relationship between the length and the deep section. You remember loading that simple timber section and how you turn it around to resist loads. That's what's going on here. So one of the earliest ways of doing that was, instead of making a huge great steel web in the center here, you can take mass away from the web where you don't actually need it, where it's not working for you. And a clever way of doing that they learnt very early on was to simply cut that web in this fashion here, lift the two sections, lift the two sections apart, and then weld them back together again, giving a deeper section here and taking mass away, in other words dead load, away from the building. And a more advanced version of this is the perforated beam. As you can see here, we've now got large holes perforated into the beam. You can almost imagine, you can just about see that it's almost becoming a truss, if you remember early on. So it's a flange up here, a flange up here. The web, the two flanges are kept apart. You could imagine a horizontal section, vertical low points here, vertical rods, and a little bit of triangulation here to help stabilize the whole structure itself. Okay. You're actually now also looking at the underfloor of underside of a folded plate floor, which links all these major beams together. It's a nice image in a way, because you can see the kind of whole hierarchy of construction is actually visible. This is the major beam taking its load to the ground at each end here. This is the secondary beam, and it's cantilevering. You can see they're cantilevering off at this point to carry a little bit of floor or roof up there, and then these are rods running through, and then they're connected that way. So there's a hierarchy of structure. There always will be. So what I mentioned earlier was the idea of the truss, which is now a series of independent lattice, if you like, a lattice work. This can be steel or timber or concrete. Again, doesn't matter. The principle is the same. Here's the flange at the top and the flange at the bottom, linked together with a series of uprights. Now, the reason for the triangulation here, the cross bracing, is because, again, you remember early on, if there's any kind of lateral load on the structure, it's going to fail, isn't it, in that direction? It's going to shear. It's going to shear away. So this triangulation is going to prevent that happening. And in reality, you'll find all sorts of versions of it, but what you've ended up with here is a quite a long span, as you can see, a deep section, but a very lightweight module, very lightweight construction element, used again as a beam in repetition. You can see the hierarchy, that all the loads are coming back down to ground here on these columns. That's a major I-section girder, so there's no air taken out of that one. As you can see, that does have to be solid, but then the secondary structure is lightweight. You might just be able to see that it lands actually on the top rail, and then here's the first diagonal there. You see that. Here's a hollow aluminium section version of the same thing. Composite timber rails and folded cold steel, I think, connecting the top rail and the bottom rail on two sides here, all to generate lightness and efficiency in putting structures together. This is a concrete one. You remember I mentioned Nervy. I think this is Nervy. I might have to double check at the end of the lecture, but anyway, it is as you can see, it's actually a warehouse again. And look at these incredibly beautifully cast concrete trusses. Now there are diagonals here. There's little diagonals at the top that are just doing the job of bracing the structure. This overall shape is actually what structural engineers call the bending moment diagram for the whole building. And the same with the columns. Look, the columns are just tapering just to solve the problem of that lateral load in the structure. So instead of a deep column, as in the earlier drawings that I showed you, this is just actually tapering slightly. So that gives you the diagonal that braces the whole. It's a very elegant structure. Here's some rather nice timber trusses. And just to confuse you enormously, particularly when it comes to roofs, and I should quickly mention that sloping roof is not a silly thing. You look at kind of buildings, you think, oh gosh, modern building has a flat roof, old-fashioned building has a sloping roof. Well, there's a lot to be said for sloping roofs, and one of them is that the work of the roof, if you like, in getting rid of rain or snow, whatever else happens to fall on it, gravity is helping. Gravity is doing the job. So as long as you put some kind of waterproof membrane on top of that, the water's going to fall off. The moment you put a flat roof, you really are relying on the technology of the materials to prevent any water penetrating. So it's traditional. Anyway, here's a range of different kind of roof trusses. This is not to confuse you. You don't have to make a particular choice. It's just to show you that there are very different ways of putting them together, and over the years you might develop preferences for one or another, or one or another might solve particular problems or particular situations for you. There's a sort of cantilevering one, isn't there? There's a continuous flat surface, and so on. Here's a clever beam. It's a bridge, of course. What can I tell you about this structure? It's designed by oh my god, I've forgotten, and engineered by a company called Price, structural engineers called Price and Myers. The architects were commissioned to design a walk bridge across this river. It's in Bristol, Temple Meads in Bristol. It's called the Meads Reach Bridge, if you want to look it up. MEAD Reach, REACH Bridge. The architects said, we want something that's almost completely see-through. You know, could we make it out of glass? Could we make it out of perspex? Make it almost invisible. And the engineers said, well, yeah, it's possible, but there's a slightly different approach you can take. You want something very lightweight that you can build off-site and lift into place, right? You don't want to have to disrupt anything. You want a very easy construction process. So what they suggested was to make it out of aluminium and perforate the aluminium. Now this goes back to what we were looking at earlier on, perforating materials in order to lighten them. So what the engineers did was they looked at the overall structure. Okay, it's a folded structure, so the beam itself is, you know, it's that depth, isn't it? It's a U section, but that's the depth. The span to depth ratio is all about this, which is kind of looks like the handrail. It's folded to give it stiffness and strength. There's a certain amount of reinforcing in the lower part, and here's little miniature bridges. So there's a truss here, if you like. There's a truss here, perforated truss here, series of little perforated beams connecting through to them. So that's the overall hierarchy of structure. But they also did something very clever, which was, I'm sorry you can't quite see it here, was that they analysed how many perforations they could put in according to the structural loading that the bridge would have to endure. So as you can see, as we get down to the end here, it's actually losing its perforations, because here they needed a more solid and continuous form because all the load is coming back at these points. So they did what's known as a finite element analysis on the bridge, which I will show you at some later stage. Yeah. Now if you go back and you recall that some of the trusses we looked at earlier on, instead of having big triangles here bracing it, there's just little triangular edges for each of the uprights, okay, and that's doing the job of bracing the overall structure. And this has got a name because it was invented by Mr. Vierendeel, and so they're known as Vierendeel trusses. And if you're designing what we will look at some later stage, what we call a habitable truss, in other words, if that was a building that was spanning and these were glass openings, let's say, and you didn't want big triangles in front of the glass, this would be how you would solve it with the Vierendeel. Okay. Sorry this isn't completely visible, it's not on my screen anyway, but what it says is something we know already. Because when loaded the upper part of a beam is in compression and the lower part is in tension, a very efficient solution to spanning is a bowstring truss. So what have we got here? Here we've got this is actually a T-section steel upper member. That's in pure compression. This is in pure compression. But why not then? The lower part of this beam is now in pure tension, isn't it? This is just a rod. So it's in tension at the bottom, it's in compression at the top. So as it's loaded in this direction, as you're pushing down here, this is pulling on these tensile rods which are connected back up at each end, so it can't go anywhere. So that's a very elegant solution. Here's another version of it. This is by Charing Cross Station. So in this case the handrail, if you like, is not structural. It's just stopping people falling off the edge. The beam that's spanning is just that. Okay, that's all it is. So that's pure tension pure compression, and that's just connecting the two sides. Effectively, there's a truss on one side, there's a truss on the other side, and that's just connecting the two of them. So that's a very elegant and lightweight way of building trusses. And it's not a new thing. You know, throughout history, people have looked at ways of elegantly spanning structures. So here we've actually got a little bit of an arching structure. This is a bowstring truss, isn't it? It's very elegant. It's got very beautiful connections to it. There's a double, 2 rods at the bottom, 2 metal rods. When it starts to get really big, or really long, shall we say, we do look at bridges, of course, because the longest spans of all are achieved through these kinds of structures, where there are, as with the bowstring truss, there have to be lots of elements or parts of the structure are elements that are in pure tension. You can no longer get very long spans with elements that are either in pure compression only, or even partly in compression. You have to have effectively wire or rods or rope, so that you're lightening the load. So here we have a cable stay bridge, and the difference between a cable stay and suspension we'll show you in a minute, but suffice to say, of course, you need the height again, because you're effectively hanging the deck of the bridge off these 2 masts here, aren't you? All the loads coming back through the wire to the mast and then back down to ground again. Of course, if you remember the 4th rail bridge that we looked at earlier on, the living model, you've got a double cantilever here, haven't you? You've got 2 double cantilevers connected at the midpoint, equal and opposite loads. Now we will see, I'm not sure whether we'll see today, but we'll see later on that these sorts of principles are applied also to buildings and roofs, particularly when you need very large spans and when you have enough space to make those types of roof. We will see, again, think of it as a beam, and the beam, if you repeat that beam, if you made a whole series of those bridges, you would end up with effectively a flat roof, wouldn't you? So that's the principle. There's one in construction, which is a really beautiful sort of semi-cantilevered structure. Now there's a suspension bridge. This is Isambard Kingdom Brunel's, I think possibly the first ever suspension bridge, called the Clifton Bridge across the Severn River in Bristol, the Clifton Suspension Bridge. And what's happening here, well, you can see instead of the cables directly taking their load from the masts, from the uprights to the deck, here we're slinging a continuous line from one side to the other, and then the deck is being hung vertically off that, and that will give you an even longer span than the cable stay. It becomes even more efficient. What I'm going to do is I'm going to give you a link, and I will put this on Blackboard, to a very interesting documentary on the making of the bridge that you're looking at the moment. Normally in a lecture we would watch it, or we'd watch some of it, because it's just a rather exciting thing, but I won't be with you. But do have a look at the Asahi Kaiko Bridge in Japan and how they actually constructed it. It is, as you now know, a suspension bridge. Oh, here we are. Here's an example. This is I think this is a Richard Rogers building. It's a factory of some kind, as you can see, but it's employing that principle in this case the cable stay principle, to carry a roof. Now the reason for doing it in this case, of course, is that here you need, underneath this roof structure, it's not showing the cladding yet, of course, not showing the outer cladding, but you need a big open space. You don't want lots of columns getting in your way. You need nice big open plan areas, and that's the reason for hanging everything off these central masts. Okay. I will show you some more examples of these probably next week, actually, in the next week's lecture, when we look at the organisation of construction elements to make interesting logical structures. So, staying with effectively the beam, or the unidirectional, what we call the unidirectional spanning element, we're looking at some slabs. And again, if you were in Marylebone, you would look up and you would see this. That, I think, is my office there. So we are standing on pretty much nothing. It's cantilevering, isn't it? But that's because these beams are continuous inside and sort of balancing on that beam along there. That's a beam, we know that now. It's connecting from that end to that end. Okay. So these, instead of this being one big solid thick piece of concrete, which would add a lot of dead weight, again, it's effectively a lot of little beams, isn't it? Called downstand beams in this case. Very commonly used in construction technology is this profile metal sheets and poured reinforced concrete slabs. Now, there's a number of reasons for this. One is it's efficient way. It is linear again, so you can see the directionality of the profile sheet is spanning from one place here to one place here. So it's linear. It's a linear span. It's a composite structure, isn't it? But the good thing about it, from construction technology point of view, is that the prefabricated profile metal sheets are laid into place, and they can be up to 4 or 5 meters long. They act as a negative, if you like, for pouring the concrete into. They act as the mold, and they stay there. So you've got a permanent mold instead of building a timber construction, formwork or something like that. You've got a permanent mold here, but it's also metal, isn't it? So it's taking some of the tensile strength of the floor. This is reinforced. This is concrete. There is some reinforcing. You'll see there's also a little bit of reinforcing going in. So there's some steel rods to integrate with the concrete itself. This is right underneath it, isn't it? But all in all, it acts together, and it's a very common way of pouring concrete slabs. And that's looking at the same thing from the underside. So here's the profile metal sheet. Okay. Again, here's a hierarchy of construction. This is an I-beam column. In this case, it's square section, unlike these girders, which are I-beams, which have got a longer flange, haven't they? Because we know that they're spanning, so there's a span to depth ratio. That's the primary structure. These are connecting through to that, and then so there's again always a hierarchy of structure. This is a beam. This is, of course, probably a building from the 1960s, and the roof of this building, yes, there's some gaps here at the moment, but they will be filled. There will be glass, won't they? The roofs are great big folded concrete sections forming the beam. But again, let's understand that the span to depth ratio is from that point to that point. That's how deep the beam is. The folding of it, of course, is giving it structural stability, isn't it? So it's a fold. Any kind of folded structure will give it that, but that's the span to depth ratio. So it's a very long span right across to the other side over there. It's a beam, and that's just a small version. This simple corrugated steel plate is just a small version. It's just another version of that, and this is actually the most common roofing material in the world. We used to call it corrugated iron. It's actually now corrugated steel. The process of making it is you take a flat piece of steel and you could run it through a series of rollers, little wheels that form that corrugation. Now that gives you just that little depth there, gives you the span to depth ratio, gives you some stiffness and span to depth ratio. It's a very cheap, common way of keeping the rain off roofs, and it is structural. And here's another folded, in this case reinforced concrete folded roof structure, which can cantilever. Isn't that elegant? Again, that's giving you the depth. The depth is there. Each one of these is an independent I think cast in situ, actually, concrete U-section. It's beautiful because, again, the roof is absolutely visible. I know that, again, this is a mid-century, mid-last century kind of a structure. But there's a great elegance about it because the structural form, the way it's working is visible to you. It's a series of U sections. There's the beam. That's the depth. That's giving you the depth. That's keeping the rain out. But that altogether is giving you one homogeneous structure, and is just through the rebars is connected to the columns. And look how slim the columns are. Very slim and very long, just to carry that structure up there. There they are again. What else can we see about this? Of course, we can see it actually was cast in situ, wasn't it? Because we can see the imprint of the timber planks that the concrete was cast into, all the timber planks. So there was a great big timber structure around here to pour these concrete sections into, wasn't there? And then they take them away. It looks sort of like a timber roof. So finally, so all of those, as you can see, again, these are linear structures. This is spanning from one side to the other, and it's just repeated, 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 as was, our structure back at our university. Repeated, repeated, repeated. If you want to build a roof and you can't necessarily take load to ground at very obvious places, you might have difficulty in bringing the load down, you will probably just do a continuous deep reinforced concrete floor section, as in this case here. Okay, you can almost see here it's not yes, I mean there are columns on the corners pretty much. Oh, there's a deep one. We know what that's doing now, don't we? Resisting the lateral load. And there's another couple of them in the middle there, but they're sort of a little bit all over the place, which is useful. There's the underside of that floor. It's very simple. It's kind of common technology throughout the world. Again, you can see that there was a timber formwork here. You can just about see the imprint of the probably timber plywood panels that the concrete was poured onto. Oh, and again, just a reminder, every time we talk about concrete, we do mean reinforced concrete. And the reinforcing, these are the rebars, just to give you some idea of the size and scale of the things. There's an awful lot of steel in concrete. Here's an interesting technology. We call it bubble deck only because I'm not sure that there is a generic term. The bubble deck is actually a trade name, I think. But as you can see from what's written there, this is the same principle, taking dead load out of the construction element. So remember earlier on we saw a beam that was castellated, then we saw a beam that was perforated. So this is a sort of three-dimensional version of that, isn't it? We've now got hollow plastic spheres inserted into the floor to take away mass where we don't need it, where it's not working for us. That gives us bigger span to depth ratios for the floor. There are still rebars, of course, still steel reinforcing, but as I said, this gives you a much bigger span because the floor is overall, it's deep, it's a deep section, but it's much lighter than it would have otherwise been. Okay. So this is again a new sort of more common way, and let's face it, we do have to minimize the amount of concrete that we're using in structures, so this is another way to help you do that. Funny enough, when you draw a section through it, it would look a little bit like a perforated beam, wouldn't it? If you understand. You can crisscross, with concrete with a series of concrete beams, and you can cast that as a continuous slab, can't you? Which is rather nice. You can call it the waffle principle. And here it's shown, but it's being picked up at certain points. But actually, you could take the load of this slab, becomes one big homogeneous thing once you've cast it, and you can pick it up in all sorts of places. You could almost cantilever with it. I'm sure you can. That's the same principle working with timber, and that's the same principle working with glass. That was the Apple building in New York, but Steve Jobs, when he was still alive, decided there was too many little bits of glass, so he's now built one that's got even less glass. I don't know if he lived to see it. I hope he did. So this is going back, I think we showed this earlier when we were looking at columns. This is Mies van der Rohe. This is the roof of the museum in Berlin that I talked about earlier, and those very elegant, remember those very elegant cruciform columns. So that entire roof, that's a waffle slab, isn't it? But it's steel, so it needs the depth because it's got its very big span, if you like. Here all of this corner is cantilevering, isn't it? So that's what 1, 2, 3, 4, 5 from the edge. 1, 2. So over here will be the next column. So you could triangulate that edge. That whole section is cantilevering. That's the beauty of this structure. You can pick it up anywhere, carry the load anywhere. You've got a continuous, effectively monolithic roof structure. This one was actually pretty heavy. I think, I may be wrong, I think they built that on the ground, hoisted it up and onto the columns. I think this might, yeah, okay, so not uncommonly, architectural technology borrows from other industries, particularly industries that are very good at designing efficient, lightweight structures. So we look to Formula One, we look to yachting, and we look to aircraft structures. And all of those use this principle here. It's called the monocoque principle. Now what we've got now is we've got a lattice work, if you like, of waffle structures inside, and then there's a skin. Now the skin is part of the, if you like, it's part of the overall structural form. So all of the lattice work is mainly working in compression. The skin works as a kind of tensile wrap around the structure. Now this has proved very useful in architecture, building monocoque structure. So here's a lovely example by is it Alfred Hoyle Monaghan, I think. Oh, you can tell I'm not very good with culture, but anyway, it's down in Bexhill, south coast of England. It's part of the famous Delaware Pavilion down there, which is a classic mid-century modern building in itself. You would look at that originally and think, oh gosh, what was it, concrete? Oh no, it is actually, yeah, it's this timber lattice, and the timber lattice has been skinned with actually a very thin layer of plywood, and then heavily painted or sprayed to prevent any kind of deterioration. Here's another beautiful example of it. This is the Lord's Media Centre, just up the road from where we are now, actually, or from where you might be now in Marylebone. This is designed by Future Systems. It was built by shipbuilders, actually, as it happens, on the River Thames, in a series of sections, as you can see here. It's all aluminium. It's a monocoque structure. It's got the internal ribbing and then the outside skin, stressed skin, working in tension as an overall structure. Very elegant, very lightweight. I won't go into this in a great deal of detail now, but you know, the prefabricated monocoque panels do exist, and these are a very light, clever way of putting structural form together. And now we can do it with plastics, of course. FRP stands for fiber reinforced plastics, not fiberglass. We talk about plastic buildings, we're not talking about the plastic that ends up in the oceans. We're not talking about fiberglass, because fiberglass is the tensile reinforcing of plastic. We will talk about plastic in detail at some point, but suffice to say, it's got a foam core, and around that core is resin, which stiffens the material. So it's another kind of stress skin structure. If you like, this is you could imagine this to be a very large surfboard. That building is actually in California, so hardly surprising, but very light, very efficient way of putting buildings together, and a way that nautical engineers have been building yachts for a very long time. So we're borrowing these kinds of technologies for large lightweight spans, and now bridges are being made from FRP off-site, lifted into place if you don't want to disrupt the road or rail that you're building across. And I think finally, in terms of multi-directional spans, in England we tend to call them space frames. Around the world they're also known as space grids. But again, if you go back and think that the bubble deck was a three-dimensional version of the perforated beam, the space frame is a three-dimensional version of the open wedge truss. The easiest way to understand a space frame is this is a series of pyramids that are linked at the top and the bottom. Okay, all the points of the pyramid are linked at the top, and at the bottom there all the squares are connected. So that's the simplest way of understanding one. This is a pyramid type. There are more than just pyramid types, but again, we're looking at a structure here that becomes completely homogeneous, and you can take the load of it. Here it is being taken to ground on the outside, as it happens, but you could have actually taken it to ground at any point. So it's very useful in that way. We will talk about these nodes when we look more closely at connections technology, but that's an important, if you like, detail. Corfu Airport, for any of you that like to holiday in that direction, or any of you that might even come from there. Yasu. So this is actually a model. It's not a real world thing. It's a gentleman called Conrad Waxman, WACHSMANN, I think, Conrad with a K, who was a great pioneer of these kinds of structures. And this illustrates almost exactly what I was just talking about, which is that it becomes monolithic, doesn't it? It becomes monolithic, and it's cantilevering in all sorts of directions, and all the loads are just coming back down to these very elegant columns at this point here. And of course you can begin to do some very interesting things with space grids and space frames for that reason. They're very light. Again, it's just a truss, it's just a three-dimensional truss, so it's just a lattice work of, it could be lightweight steel, could be aluminium, could be timber. And there he is. You can go a bit bonkers with space frames, as they did for the 2008 Beijing Olympics. This is what was known as the water cube, and we talk about it for two reasons. One, these astonishing panels, which are ETFE panels, pillows, air pillows, very lightweight panels that skin the building. But it's a continuous span. The roof is spanning continuously from the walls. Now the whole thing is a kind of dense web of space frames. So it's no longer now rational, is it? It's no longer symmetrical. But it's still the principle applies. It is effectively a space frame. Here they're using, is it hexagons or, I'm not sure, hexagons, yeah. Or pentagons or hexagons, or probably a combination of the two. But it's the depth again. It's the depth. The walls are made the same way, and you'll often see that too. That the whole thing becomes a kind of space frame, vertical, doing the vertical and horizontal work for you. It so happens that I showed you a node earlier on, which is a kind of bolted together node. It so happens that the Chinese had an awful lot of welders. So all of these nodes are welded connections, and of course the sphere often solves the problem. When you've got a lot of things meeting, coming in at funny angles, you do need that sphere at that point of intersection. Solves all the problems for you. Here's a fairly recent one. One of my students actually sent me last year. I think this is in Athens or just outside Athens now. A very beautiful, long spanning roof, and it is actually a space frame, although you can't see it. Inside it's a space frame. Can't remember quite why I'm showing you this, but I think it's the same principle. Oh yes, it is. The airport, it's a new airport. Is it the new airport in Beijing? I'm not sure. I think it possibly is, which is employing the same principle on a very large scale, the space frame principle, for large lightweight spans. So yeah, look, I'm glad I've got this, but again, as you can see, I'll put it separately onto Blackboard so you can have it in front of your computer, just sitting there in front of you when you're looking at your computer. It's what I've talked about all throughout this lecture, the importance of the span to depth ratio of beams and slabs. We call it rules of thumb because this is, in terms of detail, if you had a structural engineer looking at any particular material and any particular situation, you would drill down into it, but this will do, in other words, for your general understanding of span to depth ratios according to the kinds of materials and the kinds of construction technology that you are using. Thank you very much. See you next week.